Hello, we're going to try to simulate a soundboard with a bridge, and then the bridge is attached to a string, and the string is being struck by a hammer. The bridge looks like this. It's a 0.5 meters wide, 1 meter long, and the bridge is up here at about 0.85 meters. The string that's attached to the bridge is designed to be something like a C2 key string. It's got a harmonic, first harmonic or a fundamental of 65 hertz. And then here's the center of the soundboard. We'll take a look at how that dynamics behave there. Okay, let's start it. Okay, we have struck this string with our hammer at about 1/8 of the speaking length. The string is about almost 1.5 meters long, and we're looking at the amplitude of the string along the string. And down here I'm showing the force of the string on the bridge. Over here's the bridge. Over here's the graph. And also showing the soundboard over here with the bridge in blue. It's 1 meter long and 1/2 meter wide. And I've got the soundboard broken up into grid points. There are about a couple thousand of them. And I'm going to calculate the displacement of the soundboard at every one of those grid points. Okay, we start out, the slope of the string at the bridge over here is 0, therefore there's no force of the string on the bridge. The pulse has been generated by the hammer strike, and it'll start to propagate to the right. There it goes. And here we are, 6 milliseconds into the simulation, and still the slope of the string over here is 0, force is 0, no activity over here. Okay, now the pulse hits the bridge, starts to pull up on the bridge, so the force is positive, starts to rise. You can see there's some displacement here, right around where the bridge is located, which you would expect. Okay, now the string reflects off the bridge and inverts, and now you see the string is pulling down on the bridge, so we have a negative bridge force, and you can see some activity over here. The first pulse is starting to propagate down the soundboard. Okay. All right, the pulse has been reflected off of the bridge and passed it, and now the slope at the bridge is 0. So the force of the string on the bridge is 0. And now we have some activity over here as these waves are moving back and forth in the soundboard. Okay, so we don't have any more activity at the bridge because the slope is 0, but we have some activity on the soundboard. This pulse, these waves have been reflected or moving back up. Now, for example, over here the string pulse has reached the bridge again. We have a start of another pulse in the force. So by this time, at 33 milliseconds into the simulation, we have 2 whiplashes in the force. In other words, it goes up and then it comes down and then goes back to 0. And these pulses are about, let's see, where's this one? 23.8, let's say. And this one is at about 8.6. So what did I say, 23.8 minus 8.6. So they're separated about 15 milliseconds. And therefore, if I divide that by 1,000, and then I invert it, I get about 66. So that pulse, the series of pulses here, are separated by 15 or so milliseconds, which corresponds to a frequency of about 66 hertz, which is the fundamental frequency of the C2 string. Okay, we have some activity over here. Let's continue. Over here you can see the movement of the waves in the soundboard floor. Okay, the pulse has reached the bridge again. We've got a third whiplash. And now we've completed 50 milliseconds of simulation, which is all I'm going to do graphically. And this is the status of the soundboard at that point. And we have 3 whiplashes. And now we're going to take a look at the results of the whole run, which lasts for 1 second. Okay, here is the force of the string on the bridge, which we showed before. For example, here are these whiplashes. This is all these pulses over 1 second of simulation. Here's the line spectrum of this wave. And you see it's got a first peak here at 65 hertz, second peak at 131, which is the second harmonic, and then you see how it kind of tails off at the high frequencies. So this is the line spectrum of the force of the string on the bridge. Here's the same thing for that displacement point in the center of the board. We're looking at the displacement at one point, and you can see it's a different looking wave as compared to over here. And that's because the soundboard has got its resonant frequencies, and so it's going to be just stimulated by this wave here, but it's going to have its own fingerprint because it's got its own resonant frequencies. Down here is the line spectrum of the displacement at that one point on the bridge, on the soundboard. And even here you can see the power, it tends to tail off pretty quickly as the frequencies go up, whereas we've got the power staying rather high, almost up to about 400 hertz. I'm plotting the line spectrum in decibels versus frequency. Okay. Here is the line spectrum of the average soundboard displacement. In other words, at every instant of time, I take an average over the whole soundboard of the displacements, and then I keep that average, and then after the simulation is over, I go back and find the line spectrum of it. And I get this kind of a spectrum here. The alternative is to keep the samples at each spot on the soundboard, and after the simulation is finished, calculate the line spectrum at each of those points and then average that. Now the advantage, or I would say the downside of using this average up here, where I take the average soundboard displacement at every instant of time, is there can be some cancellations. This is especially bad idea if you're going to look at the string and take the average string amplitude and keep track of that and take the line spectrum of that later on. It's quite bad because there'd be a lot of cancellations of especially the even harmonics. Same thing could probably happen here with the soundboard displacement. So it's better to collect all the soundboard displacements at each of the grid points and then calculate the line spectrum for each of those points on the grid and then take an average. So if you compare this spectrum with that of the bridge, you can still see that there's some attenuation in power as the frequencies go up. For example, here we have 1, 2, 3, 4, 5, 6, 7. The 8th component here is a little bit attenuated compared to the previous 7, probably because that's where the string was struck, 1/8 of its speaking length. And there's a similar thing over here, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So the soundboard is somewhat of a low-pass filter compared to the bridge. All right, let's take another look here. Here is the surface standard deviation. In other words, I'm plotting width versus length, and I'm looking at the activity at every point on the board. And you can see, for example, the most activity is back here where the bridge is located, 0.85. And then we have peaks or humps here at various points on the soundboard surface that get a little bit more activity than their neighbors because of the nature of the vibrating string and its harmonics. And I think this next thing is going to be the sound of the average displacement. No, it's going to be the tone center. All right, we talked about the tone center many times before, but the tone center is the frequency about which the sound power in a wave is centered. So for example, if I look at this tone center of the bridge, you can see it varies around 200 hertz. It's higher because we mentioned earlier that the soundboard is kind of a low-pass filter compared to the bridge frequencies. Here is the average soundboard, where that's the case where I take the average soundboard displacement at every instant of time. I'm exposing myself to cancellations. It has a low frequency tone center, and then if I take the average line spectrum from all of the points of the grid, I get a number in here, which is a little bit in between. So again, this is consistent with the idea that when the wave passes from the bridge to the soundboard, there's some loss in power in the higher frequencies. This is supported with the cumulative line spectrum, which may be kind of a subtle concept to some of you, and I won't go over it. It's in the book, it's in the courses I present, and it's also in that series that's going to appear or has appeared in the Piano Technician's Journal. But anyway, here's the cumulative line spectrum. You can see that the average soundboard, which is given by this orangish curve here, most of the power, about 75%, is at the fundamental, about another 20% at the first or the second harmonic, and then not much at the higher frequencies because there's a lot of loss of power at the higher frequencies when the average soundboard signal was looked at. Here is the bridge. You see the bridge comes up slowly because there is power at the higher frequencies. And then in between again is this average cumulative line spectrum taken over all the grid points. Now I think the next one's going to be the sound from the wave. Yeah, that's the sound, and it's to be compared with the C2 from my Yamaha piano here. Okay, so that is the analysis from the spectral point of view. Here, for example, is the autocorrelation of the average soundboard displacement. That's the one we don't like. You can see the idea is to find the location of the first and strongest peak, which is right there, which is at about 15 milliseconds, which back calculates to a frequency of 65 hertz. So it says the pitch is 65 hertz because we've mentioned earlier, not in this presentation, but in earlier presentations, that we are using the first to the strongest peak to tell us what the pitch of the wave is. Here's the same thing for the bridge force. Autocorrelations look a little bit different, but has a peak, same spot basically. Around 15 hertz, 15 milliseconds, it back calculates to 66 hertz. So that completes our analysis of the soundboard, the string, and the hammer dynamics. Thank you for watching and listening.